Assalamualaikum and good day everyone. We are Group 6 and today we are excited to present our Math 2 assignment. Our focus is on solving practical problems, specifically looking at how limits work in the real world. We like to thank you our lecturer, Technologist Dr. Gede Pramudaya Ananta for his guidance. Now, let's jump straight into the first concept. What is limit? Okay, so this is our group member. First is Ahmad Suryadi, Syafir Azri, Adam Hakimi, Muhammad Halim, and me, Muhammad Fatul Ikhwan. Okay, so this slide I want to explain about defining the concept. So, what exactly is a limit? Essentially, a limit explains how a function behaves as the input gets very close to a specific value. The most important thing to remember is that we are necessarily focused on what happens at the exact point. Instead, we are looking at the trend or the direction the function is heading. This is a powerful tool because even if a function is undefined or broken at a specific spot, we can still determine the value it is trying to reach. You might wonder why we bother with this. Well, limits are the foundation of all calculus. They allows us to study continuity and change. Without limits, we would have derivatives to measure rates of change or integrals to understand accumulation. They are the building blocks for everything that follows. Now that we understand the basic idea of a limit, let's look at a more specific scenario. One-side limits. Sometimes a function behaves differently depending on which side you are coming from. Think of it like two people walking toward the same point from opposite direction, but they might end up at different heights. As you can see on the slide, side limits describe the behavior of a function when we approach a point from only one direction. There are two types. Left-hand limits, we approach the target point from the left smaller values. Right-hand limits, we approach from the right larger values. Here is the golden rule of calculus. For a limit truly exists at a point, both the left side and the right side must agree on the same value. If they approach the different values, we say the limit does not exist or D and E. Okay, so you can see the example of the limit at the right point.
Hi everyone, let's start by looking at infinite limits. Usually, when we talk about limits, we're looking for a specific number the function settles on. But sometimes, a function doesn't want to settle it, just keeps growing or shrinking forever. Take a look at the receptional function. Function x equal to 1 per x as x gets closer and closer to 0 from the positive side. The value of the fraction doesn't stop at 10 or 1000 or even a billion. It increases without bound. We describe this explosive behavior by saying the limit is infinity. You'll almost always see this happening around vertical asymptotes where the graph shoots straight up or dives straight down. Next, we have the limit laws. These are essentially your shortcut toolkit. Calculating a complex expression all at once can be messy and prone to errors. These laws allow us to break a big problem into smaller, bite-sized pieces. For example, if you're looking at the limit of open bracket x power 2 plus 3, x close bracket, you don't have to guess you can split it into the limit of x power 2 and the limit of 3x separately. By evaluating these simple parts and adding them back together, in this case 4 plus 6, we get the final answer of 10. Whether it sums product of quotients, these laws keep your work organized and accurate. But what happens when the math is too messy for simple laws? That we bring in the pressure with the squeeze theorem. Squeeze theorem, sometimes called the sandwich theorem. This is perfect for those stubborn functions that oscillate or behave wildly, making them hard to evaluate directly. The concept is simple. If you can trap your difficult function between two simpler functions, an upper one and a lower one, and both of these simpler functions are heading to the same value, then your middle function has no choice but to go there too. In the example on the slide, x power 2 is trapped between negative x and x near 0. Since both negative x and x head towards 0, x power 2 is squeezed into the same limit. It's a powerful way to find certainty in a complex mathematical neighborhood. Thank you.
Assalamualaikum, my name is Muhammad Halim. My matrix number is 250118. Okay, the first slide. Okay, let's look at the first slide. First problem, we are asked to evaluate the limit as x approaches 3 of x equal to minus 9 divide x minus 3. The numerator can be vector into x minus 3 and x plus 3. When we substitute the back, the fraction become x minus 3 and x plus 3 divide x negative 3. Since we only press 3, not exactly equal to 3, we can cancel out the x equal x minus 3. So that leaves us with x plus 3. Now, as x approaches 3, the expression approaches 6. So the final answer is, therefore the limit is 6. Okay, we move on the second problem. We need to evaluate the limit as x approaches 0 of sin x divide the x. This is very important. Result in calculus, often called fundamental trigonometry limit. Using the derivation approach, we can rewrite it as limit x approaches 0 cos x divide 1. Substitute x to 0 equals 0, we can get cos 0 equal to 1. Therefore, the limit equal 1. So, this result is correct because it is formed for the foundation for too many different rules in trigonometry. So, at the second question, the answer is 1. That's all for me. I give to my friend.
So I'm Muhammad Gani Benjar Razan. I will be presenting for question number 3, 4 and 5, which asks us to evaluate the following limit. The limit given is 5x to the power of 2 minus x plus 1 over 2x to the power of 2 plus 7. To solve this, we first observe that both the numerator and denominator are quadratic expression. The highest power of x is x to the power of 2. So we divide every term by x to the power of 2, which you can see we divide them Now, as x approach infinity, the fraction 1 over x the power of 2 and 7 the power 7 over x the power of 2 all approach 0. This simplifies the expression to 5 over 2. Therefore, the limit is 5 over 2. So next, we move to the question number 4. We are asked to evaluate the limit 1 over x plus 2. To understand this, we need to look at the behavior of the function as x approaches negative 2. Notice that the denominator becomes 0 when x equals to negative 2, which means the function has a vertical asymptote. From the left hand side, as x approaches negative 2, the denominator is slightly negative, so the fraction tends toward negative infinity. From the right hand side, as x approaches negative 2, the denominator is slightly positive, so the fraction tends forward positive infinity. Since the left hand and right hand limits are not equal, we conclude that the overall limit does not exist. So next, we move to the question number 5. The problem asks us to evaluate the limit x the power of 2 sine 1 over x. To solve this, we use the squeeze theorem. We know that negative 1 less than sine 1 over x less than 1 multiplying through by the x the power of 2, we get negative x the power of 2 less than and or equal x the power of 2 sine 1 over x less than or equal x the power of 2. Now as x approach x, both negative x the power of 2 and x the power of 2 approach 0. By the squeeze theorem, the middle expression must also approach 0. Therefore, the limit is 0. In conclusion, even though sine 1 over x oscillates infinitely as x approaches 0, multiplying it by x the power of 2 forces the whole expression to shrink to 0.
In this slide, we can see how limits are applied in real life situations, especially in cooling and heating process. When an object is hot, its temperature does not drop instantly. Instead, it decreases gradually over time until it reaches the surrounding or room temperature. This concept follows Newton's laws of cooling, where the rate of temperature change depends on the difference between the object and its environment. So, in mathematics, we use limits to describe what happens to the temperature as time approaches infinity. In this case, the temperature will eventually stabilize and become equal to the surrounding temperature. Let's look at an example. We are given the function t of t equals 25 plus 75e to the power of negative 0.1t. To find the final temperature, we evaluate the limit as time approaches infinity. As t becomes very large, the exponential term e to the power of negative 0.1t approaches 0. So, the equation becomes 25 plus 75 times 0, which gives us 25 degrees Celsius. In conclusion, this shows that the temperature will stabilize at 25 degrees Celsius, which is the room temperature. This example clearly demonstrates how limits help us predict long-term behavior in real-world situations.